how do you get the entire load deformation behavior? So, as we can see, now our goal is to get the entire P delta curve. So, P stands for load and delta stands for deformation. Now, I need to choose the strain in the concrete. Again, we have studied that in a stress strain curve for concrete, you will see that this is the way the stress strain curve is going to be assumed to be parabolic, right. So, this is f prime c and this is epsilon prime c, which is typically taken as 0.002. So, what I do here is I select different values of strain like this and then I calculate or the stress. Now, how the stress and strain are related? Again, strain in pre-stressing steel or normal steel, epsilon s is nothing but equal to epsilon c, and epsilon p will be equal to epsilon c plus delta epsilon p. These are your compatibility conditions. So, always we know that if you want to get the entire load deformation of the member behavior, we need to invoke all the three fundamental laws of mechanics, which is equilibrium of forces, compatibility of strains, and then the material that what we are using should follow some constitutive relationship, and this is for stress strain for behavior of concrete in compression. Okay, this is for concrete in compression. So, this is what we are going to do. First, we have to choose one value of epsilon c. For example, in this case, let us say, or maybe this case, I take this value equal to 0.001, for example. That is the value that I am going to choose. So, the moment I choose the value of concrete strain epsilon c, right, now I can also use this compatibility conditions to find out what are the strains in the non-prestressed steel and prestressed steel. Now, this is what we have explained. So, the moment you choose your epsilon c, I can calculate my stress in the concrete using the constitutive equation. This is what the constitutive equation that typically we use, which is a parabolic model. Parabolic model for concrete in compression. So, what is epsilon prime c? Epsilon prime c we take as 0.002 for a normal strength concrete for f prime c, which is less than 40 megapascal. We take epsilon prime c equal to 0.002. So, this is the formulation for this model. So, the moment I fix my epsilon c, epsilon prime c is given to you, f prime c is given to you. So, I can calculate for any given strain what is the stress in the concrete Fc, right. So, this we get it. Now, what is the overall thing? As again we have said, in a member like this, when I am, let us say, applying a tension like this, right, the strain distribution, if I take a cross section like this, right, maybe. So, let me write it. Okay, and your strain distribution is going to be constant. This is your epsilon, let us say epsilon c. The strain distribution across a cross section is going to be same, right. So, if this is, let us say this is a cross section that I have some steel, right, let us say AS. Okay, that means the strain in the steel epsilon s will be equal to epsilon c, that what I am assuming, right. So, if you have a pre-stressing steel, then epsilon p will be equal to epsilon c plus delta epsilon p, and this is your initial strain that we already discussed. Okay. So, for any given value of strain, now using the constitutive equation of concrete in compression, now I can take what is the strain in concrete. Now, how about in tension? Tension, we assume that the concrete is not going to do anything, right. So, this tension, it cannot take anything, quickly it will crack. So, the stress strain relationship for concrete in tension is assumed to be negligible, and it is not really going to contribute, or you can also assume some tensile strength, assuming that in tension it is going to have linear elastic stress strain response like this, right. So, the same curve I can extend it like this, and then it is going to crack, and this we can say that f prime t, which is typically we take it about 0.1 f prime c. Okay. Now, so next step is to find the corresponding strain in the reinforcing steel and the prestressing steel through compatibility condition that we have discussed. Now, what are the compatibility conditions? So, that we have already assumed epsilon c is equal to this epsilon s, right. So, strain in the steel is equal to the strain in the concrete, that what I have assumed. So, I can find out epsilon s. Then using the constitutive equations for this here, I am assuming elastic, plastic, stress strain relationship. Okay, for normal regular rebar. Okay. So, and I am assuming that the grade of steel is 500 megapascal. So, you can calculate, and the elastic modulus you all know that for steel it is equal to 2 into 10 to the power of 5 megapascal, right. And this is the idealization. So, it is an idealized curve. Of course, you will have strain hardening and you will have plastic portion strain hardening depending upon the grade of steel, but I am assuming conservatively it is going to have a this kind of a bilinear stress strain curve response. Similarly, for prestressing steel also, and I am going to assume a elastic perfectly plastic relationship. Now, you can see that the moment I fix my epsilon c, right, then what is delta epsilon p? That is what we said, which is equal to epsilon pi. If you know what is fpi, that you divide by ep to get your epsilon pi. So, for any given value of epsilon c and epsilon pi, I can calculate what is the strain in the prestressed steel. So, the moment I calculate my strain here, I can go back and calculate what is fp, which is the stress in prestressing steel, right. So, I get my stress in the prestressing steel, right. Here I am assuming again elastic perfectly plastic just to illustrate the concept. So, first we assume epsilon c, we find out what is the stress in the concrete. Now, using compatibility conditions, I can find out the stress in the mild steel or a non-prestressed steel and prestressing steel. Now that we got all the stresses, we can use the equilibrium condition because this is an axial load. Now, the axial load will be resisted by concrete, non-prestressed steel and prestressed steel. So, and this is basically your PC, this is your PS and this is your PP, where P is for prestressing steel, S is for a normal steel and C is for concrete. Now stress is known, stress multiplied by area will give me force. So, that is what we are actually doing. So, then with this then what I get is for 1 epsilon c, I got one value of n, which is an axial load. Now, what will be delta deformation is nothing but strain multiplied by length of the member. So, I get one point which is delta 1 comma n1. So, then I have to repeat the same process by increasing the value of strain in the concrete, and again using compatibility find the strain in the prestressing steel and non-prestressed steel and find the stresses and use the equilibrium equation to get your load resistance, the total load resistance, right. So, this is what the process what we are going to do. This is also called as a strain controlled approach because we are keep increasing epsilon c from, let us say, from 0.001, then 0.002, then 0.003 and 0.035, like that, until the ultimate strain that what you think is appropriate, right. So, that is why it is called strain control. So, the moment for each values of this, you get your one value of delta 1 and one value of your n1, right. Then you can plot the entire load deformation curve. Okay. Let us now we can look at this. This is the way that we plot the entire load versus deformation curve of the member. Now, let us look at one example. How do we actually calculate the entire load deformation response, and I am taking a cross section of 300 mm by 600 mm, and we are going to take 3 cross sections. The 3 cross sections are non-prestressed section with a non-prestressing steel of 2700 mm square. That is the first case. Next, fully prestressed section with a prestressing steel of 790 mm square. Next case, partially prestressed section, that means fully prestressed means there is no normal steel, there is no non-prestressed steel, it is only prestressing steel. The third case is a partially prestressed section with a prestressing steel of 1350 mm square and a prestressing steel of 395 mm square. Now you can ask me why is that I have taken these numbers. Now you see what are the grades of steel that we have taken? Fy of 500 megapascal and Fpy of 1660 megapascal, right. So these are the values. Though your Fpk is 1860, I am assuming that it is going to have a elastic perfectly plastic behavior with an yield strength of this 1660 megapascal. Now in all the three cases, I want to make sure that the tensile strength, how do we get? Area of steel multiplied by Fy. In the first case, let us say AS1 into Fy, this should be equal to AP1 into Fpy. The second, this is the second case. So this is your AP1 and this is your AS1, right? And this should be equal to, now let us say this is AS2 and this is AP2. So this should be equal to AS2 multiplied by Fy plus AP2 multiplied by Fpy. So what does this indicate? All the three sections are having equivalent tensile strength. Area multiplied by the yield stress gives me the tension strength. Of course, we have not adopted the material safety factor. So all of them are going to have same equivalent tensile strength. Okay, that is why I am considering these three sections. So if you do that, you will get the same value, right. So that is the reason that we have taken, because my grade of steel is 500 and 1660 megapascal. Okay. So now let us look at this. These are the compressive strength of concrete. Again, we are taking that as 30 megapascal. So that means cylinder compressive strength. So again, I should say cylinder compressive strength. That means this is F prime C equal to 30 megapascal, right. And yield strength of the non-prestressed steel is 500, Fy equal to 500, and initial stretching is 1240 megapascal. That means what? Fpi, what I have is 1240 megapascal. Okay. Then I can calculate my epsilon pi as Fpi divided by Ep, right. Okay. So let us look at all this three cross section that what we are considering, 300 by 600, and this is the area of your steel, which is AS1 that we said, right. And the total concrete section is having area of 180,000 millimeter square. Only concrete area is 180,000 minus 2,700, which is 177,300 mm square. Next section, 300 by 600 again. Now the area of prestressing steel, which is let us say AP1, which is 790 mm square. Again, AP1 into Fpy should be equal to AS1 into Fy, because all of them are going to have equivalent tensile strength. Okay, and these are the concrete area. Similarly, we are looking at the next case with a section of 300 mm by 600 mm with AS2, I should say, and this is AP2. Okay. So now again, when I multiply with their respective yield strength, you will get same tensile strength, and this section has same cross section area, gross area, and the concrete area will be, there is slight difference will be there because the amount of area of steel is different. Now why did we take these three cases? We wanted to see if you do this load deformation behavior analysis, can we understand in terms of behavior what is the role of the steel and what is the role of the prestressing in terms of the overall load deformation response. So that is why we are taking up this case. Okay. Now what is the process? Again, now we are starting with compression. Okay. This is compression. Okay. That is why it is negative 0.001 is a strain that first we are assuming, choosing as true as a strain value. Now, strain in the non-prestressing steel as per compatible condition epsilon S is equal to epsilon C. So, this is also going to be in negative, which is compression again. Okay. Now, next you look at stress in the concrete, because the first case this is an RC section, no prestress here. Okay, no prestress here. So, I substitute my strain, which is 0.001, and then epsilon prime C equal to 0.002. Using your constitutive equation, I get a stress for a strain that is assumed 0.001 in compression. I get a stress from concrete of 22.5 megapascal in compression. Now, I got the stress in the concrete. Similarly, I need to get the stress in the steel as well. Now, what is the stress in the steel? You know, the strain is 0.001, because the stress strain curve for steel in tension and compression are assumed to be same, right. So, and yield strain for this case is going to be epsilon y, in this case is going to be 500 divided by 2 into 10 to the power of 6, which is going to be 0.0025. So, when your strain epsilon s is less than epsilon y, you can say that the stress can be equal to E s into epsilon s. That is what we are doing. Strain multiplied by elastic modulus will give me the stress, which is 200 megapascal. Again, it is in negative in tension, sorry, in compression, right. Now, what is the total load resistance? For this particular strain assumed is Fc into AC plus Fs into As. So, which is basically equal to, if you say negative 22.5 into 177,300 plus this, you get, now you see here, this is going to be, this is the value, right. So, you get this is the total value of the load resistance, that what we are getting from the load. So, this also should be negative here, because this is in compression. So, everything is in compression. So, both steel and this is compression, when you add it up you get this value, right. So, this is what we are seeing here, and if you for this, this is I have done for the other, I am showing the calculated values for the entire range. This is highest compression, okay. I am saying that this is going, it is going to fail in compression. Right. So, this is your failure strain. Here I have taken 0.003, you can take little less also, right. And this is the value that we are showing the calculations. You can see epsilon s is 0.001, again compression, stress in the concrete is 22.5 megapascal, stress in the steel is negative 200 megapascal. And how did we get the delta? Delta L? Delta L is nothing but epsilon c multiplied by length. So, epsilon c is 0.001 compression multiplied by 1000 will give me, it is negative 1 millimeter. Okay. So, that is the strain in the, or the deformation for a 1 meter length when the concrete is subjected to a strain of 0.001, and this is the load. So, this is your delta and this is your load. Similarly, I can do it for other sections also, 0.002 and 0.003 also. Now, when the strain in the concrete is 0, again strain in the steel also is going to be 0. This is in RC, all right. So, stress is going to be 0, stress in the steel is going to be 0. Now, delta is also going to be 0, because delta is epsilon c multiplied by length, and the load is basically again going to be 0, because load is nothing but stress in the concrete multiplied area of concrete, stress in the steel multiplied by area of the steel. So, when I add all of them, everything will be 0. So, you can see that for a reinforced concrete member, when there is no deformation, there is no load also, right in the origin. The curve actually passed through the origin. So, that indicates that for a deformation of 0 or a strain of 0, you have no load resistance offered by the member. Now, this, when the value becomes positive, it becomes tension, right. So, it becomes tension. So, here in this case, we are assuming that the concrete is, again concrete would have cracked at a much lower load, right. So, which would have cracked at a much lower load, but we can assume that concrete can take 10% of the compressive strength in tension also. So, that is what here we have done, okay. So, this is what we have done here. It takes a very small amount of load, then the concrete gives, and it is all the load is always taken by the steel only, right. So, that is what here. So, but this strain you can see that it is 0.001 is much larger than what you get for a cracking strain. So, corresponding to that you get a deformation of 1 millimeter in tension and the load resistance of 540. Like that we can do the calculations and I can get different values of delta and load resistance. So, this is one sample calculation that we have shown. So, like this we can do for other strain values and you can generate this entire load deformation curve that what we have plotted. And you can see here for this section the maximum load resistance is roughly about 6,500 or so, right, 6,400, roughly it is about 6,400, right. And in tension you can see that it is you are getting about how much. So, you are getting about 1350 or so, right. So, it is about 1350 kilonewton and the moment it reaches its yield strain which corresponds to 2.5 millimeter. How did we get this 2.5? When strain in tension epsilon c becomes 0.0025, then your epsilon s also will become 0.0025, which is equal to epsilon y, right. So, that is where it is going to yield. After that the steel is not going to give any additional resistance, it will keep giving that 500 megapascal stress, right. So, in this way the entire load deformation curve for a reinforced concrete member can be generated. So, you can see here these are the stresses that you get. So, what is that we can infer from here is in compression it is a concrete that is actually giving you the most of the load resistance and the steel, because the area of steel what we are putting is very small, my load contribution from the steel is going to be less. So, whenever I need compressive resistance I need to put more area of concrete than the steel. But for steel when you look in tension, when you look at it, you see here the stress offered by concrete is always 0. That means the load offered by concrete is also going to be nearly 0 at high strains, right. So, if you want tensile strength then we need to put only more area of steel in tension. So, that is what we have studied in advanced RC course as well. This is the way we generate your entire load deformation behavior. This is for a pure reinforced concrete section. Now, let us look at let us repeat the same problem for a pure prestressed section. So, this section does not have any non-prestressed steel, you have only prestressed section with only AP equal to, we have seen that, which is equal to let us say, right. So, this is 790 mm square. So, okay. So, for the same cross section now let us look at now if I choose a concrete strain value of 0.001, again it is in compression, we are doing the calculation only for compression, but you can easily create an Excel sheet and do for tension as well. So, this is the again stress strain curve for concrete. So, we are looking at this particular strain, right, epsilon c equal to 0.001 and which gives me stress equal to 22.5 megapascal. Fc equal to. So, that is what we are doing, okay, for this. Now, what is delta epsilon p, which I have said initial stress, which is equal to Fpi. When I do this 1240 divided by 2 into 10 to the power 5, I get an initial strain of 0.0062, that is in tension, this is in plus. So, this is always the initial thing for steel, you stretch the tendon and you leave the tendon to go back to its original position. In that process it is going to squeeze the concrete and going to put it in compression. So, that is the basic idea of prestressing. So, we have discussed that. So, steel is always going to be in prestressing steel, the initial condition it should always be in tension. So, this is an initial condition, right. Now, what are the strain in the prestressing steel? If I assume strain in the concrete to be 0.001, this is epsilon c plus delta epsilon p, this is a compatibility condition that we talked. So, the strain in the concrete is negative, this is in compression and the steel is in tension. So, this is the most important point. So, when I add them up, the net tension in the prestressing steel is still in positive value, which is tension only, right. So, though the prestress section is subjected to a compressive strain of 0.001, but if you look at the net strain in the prestressing steel is still it is in tension, right. So, that is the most important thing that we need to give. So, the stress is going to be now 0.00502 multiplied by 2 into 10 to the power 5, then I get 1045 megapascal. So, the steel is still in tension. So, this is plus, and the stress in the concrete we already did it, which is 22.5 megapascal. Now, using equilibrium condition, this is PC, this is PP. Now, PC is negative 22.5 times the area of the concrete, which is 179,210. Then this, if you see, this is plus. So, this is in tension. Though the entire load applied is in compression, now pre-stressing steel is offering only tension, right. So, that is 1045 multiplied by the area of pre-stressing steel, this is your AP, right, this is your FP. FP multiplied by AP will give me this force of 3206.7 kilonewton. So, this is again for one value. Now, what is delta? Delta is nothing but same, epsilon C into L, which is 0.001 times 1000, which is going to give me 1 millimeter. So, I get one delta and one load value N. So, I can repeat this process for other strains and I can get the entire load deformation behavior. So, that is what we have done here, and you can see here this is the entire response, and you can see the maximum load for this particular section. Usually it is at when the concrete reaches 0.002. In compression it has taken about 4708 kilonewton. In tension, if you see the calculations again, you can take this section is going to take about 1311 kilonewton. This is the value. So, roughly 1311 kilonewton. Okay. So, that is the tension capacity. Now, you can also calculate your cracking capacity as well. So, that we can calculate your cracking capacity corresponding to a strain. Now, how do I calculate my cracking strength? I have to assume some tensile strength of concrete F prime T, which we have taken to be 0.1 F prime C. So, that corresponds to 4 megapascal. Now, what is the strain corresponding to cracking in tension? It is going to be F prime T again divided by EC, and this is 4, and EC we know that it is 5000 square root of FCK, and F prime C, you know, correspondingly you can put your FCK value get, and typically this will be close to 0.00011 like that, right. So, this is the strain. So, corresponding to this tensile strain, if you do the calculations, I can get my cracking load, right. I can get my cracking load. Okay. So, you can do that. So, compared to the reinforced concrete case, if you see the cracking load in a pre-stress system will be much higher. Okay. That we can show it from your calculation. So, this will be basically when the strain is also 0, you know, it will be slightly higher than this. Okay. So, it will be in between. Okay. So, there will be drop and then there will be load resistance like this. So, this is the way you get your entire load deformation curve for a pure pre-stress section. So, this is again a pure pre-stress. So, what is the meaning of again pure pre-stress section? We see that this section is not having any non-prestressed steel, it is having only pre-stressing steel. That is why we call this section as a pure pre-stress section. Okay. So, you can do the calculation for the first cracking as well, because now that we got the strain epsilon prime epsilon C. Now, in this case I am taking a positive value of 0.00011. If you do the calculation for that, you get your cracking point, right. Okay. And this is the sample calculation that we did, you get 3201 mm. Okay. This is, we have shown that for one value of strain, how to get your load resistance on the deformation, and this is for a pure pre-stress section. Now, we can repeat the same value for a partially pre-stressed section. Now, again what is the condition? We have taken 3 sections which will give you the same tensile strength, right. So, let us assume again we are doing the calculation for only one strain, a compressive strain of 0.001, and now this is a partially pre-stressed section. So, it has both normal steel and pre-stressing steel. So, I need to calculate both epsilon S and epsilon P. Now, what is epsilon s? Epsilon s we know it is equal to epsilon c, which is 0.001, and epsilon p, how do we calculate that? Epsilon p is nothing but epsilon c plus delta epsilon p. So, this is in compression, again this is in tension, initial strain, then the net strain is going to be tension, which is equal to 0.0052, and Fp is going to be epsilon p multiplied by Ep, which is 1040 megapascal again, and stress in the steel, again this is in compression. Okay, the moment you see negative, it is compression, so you get negative 200 megapascal, and stress in the concrete we have already done that, which is negative 22.5 megapascal. So, the total axial load, now we got all the stresses, you know all the area, you plug in the value and you get your value of 3870 kilonewton roughly, right. And again delta corresponding to this is 1 millimeter, because delta is again epsilon c multiplied by L, and epsilon c you have taken it to be 0.001. So, you get your value. So, this is the way that we get, right, these are the values. So, now we have done the calculation for one point for all the sections. Now, you can repeat the same exercise and generate the entire load deformation curve, right. Now, let us look at how this load deformation curve is actually looking for this partially prestressed section, right. Again it has the same tensile strength. So, if you go back and calculate, it is about 1400 or so that we will see. So, this is in compression, these are the capacities. Okay. So, this in this way you can generate, and you can also calculate your PCR and delta CR. What are the cracking load and deformation corresponding to cracking load. Now, delta CR is easy. So, we have said it is epsilon CR multiplied by length. Epsilon CR is nothing but strain corresponding to cracking, which we calculate to be 0.00011 or something. You can check this value, right. So, you get your length as roughly it is about 0.1 millimeter or so. It is a very small deformation at which itself it is going to crack in tension. So, roughly it is going to be 0.1 millimeter. Okay. Right. So, in this way you can generate the entire load deformation curve for partially prestressed section. Now, let us compare all three of them. Let us see how all three of them looks, right. And this is the first thing that we did for non-prestressed section, regular reinforced concrete section, and you can see that the compression strength is about, let us say about 6500 or so, right. And cracking is about very small value, right. We know how to calculate the cracking strength for once you give your epsilon CR or epsilon prime T, right. And this is a very low cracking load in tension, very high compression load, which is 6500. Cracking load you see roughly it is about, if this is 500, roughly about 250 or so, right. Now, let us look at what happens to pure prestressed section. Now, you see pure prestressed section, what is it happening? Now, the cracking load has increased to this roughly about maybe 1250 or so, but all of them, both of them, if you see this maximum tensile strength is same tension strength, right. So, in tension, whether it is prestressed or fully prestressed or non-prestressed or fully prestressed, you get the same tension strength. But what happens to compression? When you do not prestress, you get 6500 kilonewton capacity, but the moment you prestress, the capacity in compression goes down, because why? We have seen that the rebar is still in tension, so it is going to subtract the load contribution, it is not going to add up, right. So, we can say that 6500 actually has become 4800 or so, right. So, prestressing is going to reduce your compressive strength, and prestressing is going to help me in increasing your cracking load. Prestressing is not going to really improve my tensile strength if you compare equivalent sections, right. These are the conclusions that we can make from this. Now, let us look at what is the partially prestressed. So, what do you expect the partially prestressed? It is going to have an in-between performance than that of non-prestressed and fully prestressed section. So, your blue color curve, which is your partially prestressed section, you see that again your cracking load is going to be in between that of pure prestressed and non-prestressed, your compressive strength is going to be in between that of pure prestressed and non-prestressed. So, you are going to get an average performance in between that of prestressed and non-prestressed response. So, what we can conclude from here is prestressing greatly helps in increasing the cracking strength, and if you look at it also from serviceability point of view also, let us say that I am looking at 1 mm deformation. So, 1 mm deformation at which I am calculating, if you see the load resistance offered by a non-prestressed section is less. So, right, then the next one is this blue par, it is slightly higher, but pure prestressed section it is going to be much higher. So, that means in tension prestressing is really helping in increasing the stiffness of the section, the stiffness of the member, and also for a particular deformation it is giving me more load resistance, right. So, that means your serviceability performance is also going to be much better, right. So, we can now conclude actually prestressing does not increase the ultimate load capacity in tension, okay, and I should say in tension, and prestressing significantly influences the load at which the concrete cracks in tension. That is what we have seen. This is your cracking load, okay, this is your cracking load. So, that means cracking load goes up, more prestress, more is a cracking load. At service load levels, prestressed concrete shows reduced strains and deformations in tension. That is what we have seen. If we compare it at one deformation, if I compare it at one load, right. So, if let us say if I take this load, right, let us say this load, the blue color fellow will give me this deformation, which is this. The red color fellow will give me this as the deformation, and right. So, you can see here, but this is the load resistance. So, but pure prestressed section which will not give any deformation at all, right. So, in this way under service loads the prestressing helps in tension performance, right. It is going to give you less deformations, or a particular load level the deformations are going to be less under tension when you do prestressing.